Today is the first of our 3 lectures on power in steady state sinusoidal circuits. So my goal for today is to cover instantaneous power in these systems. And then through our discussion of instantaneous power, we will kind of accidentally stumble into average power. We will then formally explain average power, and that'll be enough for today. So let's start with our instantaneous and average power title. Instantaneous and average power in steady state sinusoidal circuits. All right, so let's say that we have a source. Does not matter if it is a voltage or current source. And we connect our source to a generic network. So here we have a linear black box AC network. And we measure the time domain voltage across the terminals of our network and the time domain current flowing into our network. If we have a system that is sinusoidally excited, we would expect to see that our voltage V of t would be of the form Vm cosine omega naught t plus some phase angle theta v volts. And similarly, our current I of t would be of the form Im cosine omega naught t plus theta I amperes. So the instantaneous power, which will be a function of time, of the power absorbed by our network, or alternatively, supplied by our source, is simply going to be the product of that voltage waveform and that current waveform, because power is always just I times V, right? So V of t multiplied by I of t. And so now we're going to have to multiply those two sinusoidal functions together and see what shakes out. So this is going to look like Vm cosine omega t plus some phase angle theta v multiplied by Im cosine omega t plus some phase angle theta I. And in order to facilitate this multiplication, I am going to use a trig identity. I've used it before, but I'm going to put it up for you guys as well. So if I have the cosine of some angle 1 times the cosine of some angle 2, this is equal to 1/2 the cosine of angle 1 minus angle 2 plus 1/2 the cosine of angle 1 plus angle 2. So applying this trig identity, I'm going to get 1/2 Vm Im cosine of theta v minus theta I plus 1/2 Vm Im cosine twice omega t plus theta v plus theta I. So this is my generic expression for the instantaneous power absorbed by really anything, right? So I'm going to put a box around this. So before we look at this expression, I want to make a quick point here. Okay? The instantaneous power is a time domain function. Okay? We can see that because it's explicitly expressed as being a function of time. Okay? Just because this expression is a time domain function does not mean we are supposed to do any circuit analysis whatsoever in the time domain. Vm is the magnitude of our phasor voltage. Im is the magnitude of our phasor current. Theta v is the phase angle of our phasor voltage. Theta I is the phase angle of our phasor current. Meaning, all that I am expecting you to do is to continue doing your circuit analysis in the frequency domain where the math is easy, and then take the results of that analysis and plug numbers into this expression. Okay. All right. So what I want us to look at now is how this power function is going to look over time. So here is P of t. Here is t. So my first term, so actually let me rephrase this question. Is Vm a constant for a given circuit? Does the magnitude of the voltage change? No, it's a constant value. What about the magnitude of a current? Also a constant value. Phase angle for the voltage is a constant. Phase angle for current is also a constant. So every single term in that first portion of our instantaneous power expression is a constant value, which means our instantaneous power is going to have a constant or DC term, right? So this whole bit right here is a DC contribution to our power, okay? It is always there. And so I'm going to put here PDC, and I'm going to draw a dashed line like so. So this effectively represents a DC offset for our instantaneous power. Superimposed on top of that DC offset, we have this AC term right here. Notice that this AC term is actually oscillating at twice the angular frequency of either the voltage waveform or the current waveform, right? Because it's 2 omega t, okay? So we're going to see that our power oscillates at twice the frequency of excitation. And so I'm going to superimpose this power on top. And so it's going to look something like this. Generically speaking. There we go. All right, so slightly different question. Based on this graph, what's going on in the intervals that I've shaded in red? Other way around, but yes. So our plot here is for absorbed power. The areas that I've indicated in red are regions of time where we have negative absorbed power, which I hope at this point we all understand means that we are supplying power. So at some point in the interval here, or actually multiple points in the interval here, our black box AC network actually winds up supplying power back to the source that is exciting. So our network, for very brief intervals of time, is behaving like it's the source, and our supply is actually acting as the load in this system. And we can see that by the sign on the power over these particular parts. So this particular wave shape is characteristic of a circuit that contains energy storage elements, right? So capacitors and or inductors, okay? Anytime we have any energy storage elements in our steady state sinusoidal system, we will see that sometimes the energy stored by those elements gets to supply power back to the source. And we'll talk about this phenomenon significantly more over our next two class meetings as we investigate the concept of power factor in a steady state sinusoidal system. Okay. I just wanted to point that out to you guys because it's interesting. So let me ask a slightly different question. What does this DC offset represent in this system? So if we look at our graph here, exactly half of the time, our instantaneous power is above that dashed line, and exactly half of the time, our instantaneous power is below that dashed line. So let me ask again, what do you think the DC contribution represents? So that's what it's doing on the graph, but that's not necessarily what it represents. The average. So that DC contribution is the average power absorbed by our system. Because once again, exactly half of the time we're above it, exactly half of the time we're below it, and we have a perfectly symmetrical response here. So this DC contribution is the average power absorbed by our system, and we will more formally describe that in about 20 minutes. All right, so this expression that I've boxed in red here is generic in as much as it can work for any circuit element. So it doesn't matter if it's a resistor, a capacitor, an inductor, a combination of those three elements, a source. This particular expression is valid for all of those things. However, it requires us to know both the phasor voltage drop across our element or network of interest, as well as the phasor current flowing through our element or network of interest. So what I want to do now is I want to develop specific equations for resistors, capacitors, and inductors by themselves that might allow us to not have to know so much information so that we have kind of a quicker way to solve for our instantaneous power for those elements, all right? So let's start with a resistor, okay? So what do we know about resistors in steady state sinusoidal circuits? Well, recall from our lecture a few days ago that the magnitude of our voltage drop is going to simply be the magnitude of our current times the resistor value. And then we also know that the phase angle for the voltage drop across a resistor and the phase angle for the current flowing through a resistor are the same angle. Right? Told you these relationships were going to show up again. So using these relationships, we can say that the instantaneous power absorbed by a resistor can be expressed as 1/2. So let's put everything in terms of voltage now, okay? So Vm is just going to look like Vm. Im can be written as Vm divided by R. So Vm times Im would then be Vm squared divided by R. Now I have the cosine of theta V minus theta I. Well, for a resistor, theta V and theta I are literally the exact same thing. So what's the cosine of 0? 1, okay? So we effectively have already figured out what our average power term is. It's just 1/2 Vm squared over R, which is very similar to our DC relationship for the power absorbed by a resistor, except that we're multiplying by this factor of 1/2 because of this trig identity. Okay. So now we're getting over to the AC side. So 1/2 Vm Im is still going to look like 1/2 Vm squared over R, so that's why I factored that part out. Now we are going to have cosine of twice omega t, and since theta V and theta I are the same thing, I can express this as just twice theta V. So with this equation, I can figure out the instantaneous power absorbed by a resistor, and I only need to know the voltage, right? If I have the magnitude of the voltage and the phase angle of the voltage, I have all of the information I need as long as I have the resistor value. So I don't have to bother with solving for the current and all that kind of good stuff. While we're at it, we can say that the average power is just the DC portion of this thing. And so that's going to look like 1/2 Vm squared over R. Okay. And so we're going to do the exact same thing here, but now we're going to put everything in terms of the current. So we'll have our factor of 1/2. Vm is exactly equal to Im times R. Multiply that by Im, and we get Im squared R. Once again, this looks very similar to our DC relationship, except that we have this pesky factor of 1/2 to remember. Cosine of theta I minus theta I is still cosine of 0 or 1. Then we'll have plus cosine twice omega t plus twice theta I. And our average power in terms of only our current is then 1/2 Im squared times R. Bless you. So I want to be clear here. These two relationships are only able to be used when we have a pure resistance, right? So if we're trying to find the instantaneous power absorbed by just a resistor, either of these are fair game, and we get to choose our own adventure depending on which of the two quantities, voltage or current, would be easier to solve for in that particular circuit, right? So we no longer need both pieces of information. We can just rely on one and the fact that we know the resistor value in order to get our instantaneous power. Any questions on this before we move on to our inductor relationships? All right. So for an inductor, we know that the magnitude of the voltage Vm is equal to omega L times Im. And we know that theta V is equal to theta I plus 90 degrees. Right, so we know for an inductor that our voltage always leads our current by 90 degrees, or transversely, our current always lags our voltage by 90 degrees. And hopefully, when you guys did the lab at the end of our last class meeting, you actually found that that was pretty close to true. You wouldn't get exactly 90 degrees because the inductance has some inherent resistance because it's a coil of wire, but it should be pretty close to 90 degrees. All right, so let's figure out what PL of T should look like. Okay. So 1/2 is just going to look like 1/2 If we're expressing everything in terms of our voltage, then Vm is just going to be Vm. And then Im is going to look like Vm divided by omega L, giving us Vm squared over omega L. Now we're dealing with that cosine of theta V minus theta I, right? So theta V is equal to theta I plus 90 degrees. So theta V minus theta I is theta I plus 90 minus theta I is just 90 degrees. What's the cosine of 90 degrees? 0. What does that imply here then? Exactly right. An inductor does not absorb average power. So that first term is 0, so we're just going to go on to the second term now. We're going to have cosine of twice omega t. So I'll have theta v plus theta I. Well, if theta v is equal to theta I plus 90 degrees, then theta I is equal to theta v minus 90 degrees. And so we wind up getting twice theta v minus 90 degrees here. And I'll put this one in the middle. Our average power is simply 0. So we figured out how to express the instantaneous power absorbed by an inductor only in terms of the voltage drop across the inductor. Now let's repeat this and do it only in terms of the current. So this is going to look like PL of t is equal to 1/2. Vm is going to be expressed as omega L Im, multiply that by Im, and we have Im squared times omega L. Cosine of theta v minus theta I is still going to be the cosine of 90 degrees, so that term goes to 0. And now we'll have cosine of twice omega t plus, so we're going to express theta v as theta I plus 90 degrees. Theta I is just theta I. Add those two together, and we get twice theta I plus 90 degrees. So here's our relationship for inductors. Lastly, let's consider what happens when we have a capacitor. So for capacitors, we know that the magnitude of the current is equal to omega c times the magnitude of the voltage. And we know that theta I is equal to theta v plus 90 degrees. So for a capacitor, we find that the current leads the voltage by 90 degrees. And once again, you guys should have experimentally verified that or something close to that in our last lab. So expressing everything in terms of the voltage, I'm going to have PC of t is equal to 1/2 Vm squared times omega c. When I do my mathematical manipulation of my phase angle here, right? So I'm going to have theta v minus the quantity theta v plus 90 degrees, which is going to look like negative 90 degrees. The cosine of negative 90 degrees is also 0. So capacitors don't absorb any average power either. Okay. So moving on to our AC term, we're going to have cosine of twice omega t, and then we'll have plus twice theta v plus 90 degrees. In terms of our current, This becomes 1/2 Im squared divided by omega c times the cosine of twice omega t plus twice theta I minus 90 degrees. And once again, our average power, that looks atrocious, is equal to 0. So we now have relationships for the instantaneous power absorbed by a pure resistance, a pure capacitance, and a pure inductance in terms of both only the voltage and only the current. So what I want us to do now is to look at in-class assignment problem 2, because this is one that I get a whole heck of a lot of questions about. And it also happens to be pretty much identical to one of your homework problems. So we'll get the most bang for our buck, as it were, by looking at this particular problem. Let me get this out of the way. Yep. Nope. I don't know who keeps flipping that switch, but thank you for the heads up. Yeah. I appreciate that before it just straight up died on me. All right, so this should be in-class assignment number 22, if I'm not mistaken. We're going to look at problem 2 specifically. So in this problem, you are told that we have 3 circuit elements connected together in parallel. So I'm going to draw that out. We have the current source in parallel with a resistor, in parallel with an inductor. We are interested in calculating the instantaneous power, but I cannot emphasize this strongly enough. We are going to do all of our circuit analysis in the frequency domain. So I'm only going to bother drawing this circuit in the frequency domain. So my current source is 100 cosine 2 times 10 to the 5t milliamps. How am I going to represent that current source as a phasor current? I would, yeah. So 0.1. All right. We don't. What does that mean? Exactly right. So 0.1 angle 0 degrees amps. Our 1 kilo ohm resistor is still going to be a 1 kilo ohm resistor. What's our inductor going to look like? The impedance of an inductor is just j omega L. Okay. So omega in this case is 2 times 10 to the 5. L is 15 millihenries. And so that's going to look like a J 3 kilo ohm impedance. So a couple of things here. We are asked to calculate the instantaneous power absorbed, I'm underlining that heavily because that's important, by each of the elements in this circuit. Now, because I am either A, lazy, or B, efficient, I'm going to try to figure out how to get the necessary information in order to carry out all 3 of these calculations in the easiest possible way. And to me, that would involve simply finding the voltage drop across all 3 of these elements because they're connected directly in parallel, right? So if I can find this phasor voltage, let's just call it V. Well, that's all the information that I need to calculate my instantaneous power absorbed by my resistor, because we just developed an equation that allows me to do that. That's the only piece of information I need to know. to calculate the instantaneous power absorbed by my inductor, because we just derived an equation that would allow us to do that. And because I have a source, I'm going to have to use that generic equation that I boxed in red, but I obviously already know what the current is, so the only other piece of information I need is the voltage. So solving for this voltage gives me all of the information that I need to plug into my equations, okay? So how might I go about solving for this voltage? We could do current division, but I argue that that's too much thought, too much work. I would argue that Ohm's law is fair game, because we have a known amount of current flowing into a parallel combination of impedances, right? So using Ohm's law, I could say that my voltage V is just 0.1 angle 0 degrees amps multiplied by 1 kilo ohm times J 3 kilo ohms over 1 kilo ohm plus J 3 kilo ohms. Let me throw this in a calculator. So 0.1 times 1 times 3i over 1 plus 3i gives me a voltage of 94.868 with an angle of positive 18.435 degrees volts. So let's start with our resistor. Okay. So the power absorbed by our resistor at t is equal to 10 microseconds will be 1/2 times the magnitude of my voltage, 94.868 volts quantity squared, divided by my resistor value, which is 1 kilo ohm. This whole thing is going to be multiplied by a factor of 1 plus the cosine of, so I'm going to have twice omega. Since omega is 2 times 10 to the 5, I'm going to just put this as 4 times 10 to the 5. So that's my twice omega. T is 10 microseconds. So that's 10 times 10 to the minus 6 seconds. So omega is measured in radians per second. When I multiply that by seconds, I get some number that is just an angle in radians. My phase angle, which I'm about to get to, is very obviously in degrees. And so in order to do this calculation correctly, I'm going to need to convert one of those angles into the other form. I typically choose to convert that omega t bit into degrees because my calculator is most often just set in degree mode. So I am going to introduce a conversion factor here. So this is just going to look like 180 degrees over pi. And then I'm going to add to this twice my phase angle of 18.435 degrees. Close my parentheses. There I go. So before I throw this into my calculator, does anybody have any questions or comments or concerns about where any of these numbers came from? So we were explicitly told to find the instantaneous power at 10 microseconds, which is 10 times 10 to the minus 6 seconds. Any other questions? Walker. So that is a fantastic question. For your exam, I will provide an equation sheet just for these power relationships and all this kind of stuff. Now, I'm gonna, if you please send me an email, I will put the equation sheet up for you guys to start looking at now so that you have plenty of time to do it. Now, I want to mention something here. I did not create this equation sheet because I do not feel that an equation sheet is actually necessary for this stuff. So I'm not saying that this equation sheet is riddled with errors, but it was developed by a different professor, and so it might not match stylistically exactly what we are used to. I'm giving you that as a fair warning, and because I don't think you need an equation sheet, I'm not going to take the time to update it. So you're welcome to use it for your exam. You will be provided a copy of it with your exam. Use it at your own risk, whatever. Am I very clear about that? Okay. All right. Any other questions about this before we toss this into our calculator? Yes, Landon. Fantastic question. And the short answer is yes. So I don't know if you have a TI calculator or not. So for the TI calculator, if you go second and then pi to get the complex menu, the second option says polar angle. And so that literally just returns the angle for you and all that kind of good stuff. Option 3 is for the magnitude. And so you would just get the magnitude part of that thing as well. For those of you that have Casio calculators, the part that Landon was specifically asking about regarding the angle, if you press Shift 2 to bring up that complex menu, the argument operator, so ARG, is what's going to give you just the angle. If you wanted the magnitude of your complex number, that's just the absolute value operation, which I'm trying to remember exactly where it is on this calculator. For the Casio 115, you press Shift and then the hyperbolic button to get there. And it should be something similar to that on the Casio 991s, but I don't have my Casio 991 because I let somebody borrow it and I forgot who. So, but you can use your calculator to explicitly spit out just the parts that you need for this thing, which is exactly what I'm about to do. Okay. So I would store this thing in my calculator as a variable X, and then I would have 0.5 times the magnitude of X divided by 1000. And I'm going to save that part in my calculator as A. And so to me, that came out to be, actually, hold on. Um, 47.434 and some change milliwatts. So I'm just going to put a note here. 47.434 milliwatts. Now I'm going to do that other bit. So cosine of 4 times 10 to the 5 times 10 times 10 to the minus 6 times 180 over pi plus twice the angle of what I have as X gives me negative 0.0688. So just this bit by itself is negative 0.0688 and some change, which I'm going to store as B. And so now I will simply have A times 1 plus b and I did not get what I was expecting to get. That would actually make way more sense. Let me do that first bit again. 1/2 times the magnitude of x. Very likely I forgot to square it. Yep, I get 4.5, almost exactly. 4.5 and then a whole bunch of zeros. All right, let's try that. Save that as A. And then A times 1 plus B, 4.190, which is exactly what I was looking for. $4.190 and some change watts. So that was my power absorbed by my resistor. Now let's look at the power absorbed by my inductor. So I know that the DC part is just completely gone. So I'm going to have 1/2 the magnitude of my voltage, 94.868 volts quantity squared, divided by omega L, which is just the impedance without the J. So that's just 3,000 or 3 kilo ohms. Cosine 4 times 10 to the 5 times 10 times 10 to the minus 6 seconds times 180 degrees over pi plus twice that 18.435 degrees minus 90 degrees because I'm using the voltage. And I'm going to throw this into my calculator. Once again, I'm going to break it up into 2 smaller steps. So 1/2, yes. There is not. There should not be complex numbers in our time domain thing, right? So let me go back here and show you exactly why I am not putting a J. If we look at the equation that we are using, which is this guy right here, I am just dividing by omega L, which is the magnitude of that impedance. J should not be there. Well, what the hell? Oh my God. I did not know it would do that. So anyway, I'm simply dividing by omega L, which is the magnitude of that impedance. The J should not be in there. Okay? There should not be complex numbers in any of this stuff because we are in the time domain. All right. No, I'm reinforcing that not to pick on you, but because I've had students for the past 5 years wind up with random J's and all that kind of stuff in here because they don't fundamentally understand. Take the bits and pieces of your frequency domain stuff that you need and just plug it into the equation. Stop trying to force complex numbers into this. All right. Coming back over here. So we're going to have the magnitude of X quantity squared divided by 3,000. So for me, this part looks like 1.500 and some change. I'm going to store that as A now. Then I have cosine of 4 times 10 to the positive 5 times 10 times 10 to the negative 6 times 180 over pi plus twice the angle of X minus 90 degrees, close. I get negative 0.998. So this part looks like negative 0.9976 and some change. I'm going to call it 8. Store this as B. And now my answer should just be A times B. And I get negative 1.496, 4 and some change, which looks like I have a little bit of rounding error there, but nothing that would scare you off from thinking you did it incorrectly. Right? So lastly, we are going to find the instantaneous power absorbed by our source, okay? And to do this, we need to use our generic equation. So for our current source, we're going to have 1/2 times the magnitude of our voltage, 94.868 volts, times the magnitude of our current, which is 0.1 amps, times the cosine of the phase angle of our voltage, which is 18.435 degrees, minus the phase angle of our current, which I'm going to call 180 degrees. So some of you may be going, where the hell did that 180 come from? I would like to remind you that we are asked to calculate the absorbed power, which means the current here is flowing into the negative polarity terminal. So that 180 degrees is me effectively multiplying that current by a factor of -1 so that the current is flowing into the positive polarity terminal because I'm trying to find absorbed power, okay? So if I shift my current by 180 degrees, it's just the current in the opposite direction, which is indeed the current flowing into the positive polarity terminal. So absorbed power and supplied power will still come up and bite you on the ass for exam 3, as I said it would on the first day of class. Then we have that same 1/2 94.868 volts times 0.1 amps times the cosine of 4 times 10 to the 5 times 10 times 10 to the -6 times 180 degrees over pi plus 18.435 degrees plus 180 degrees, close my parentheses. And as per usual, I'm going to break things down a little bit. So 1/2 of the magnitude of x times 0.1. So just this part right here looks like 4.743 and some change. Let's store that as A. Cosine of the angle of x minus 180 degrees comes out to be negative 0.948 and some change. So 9486. So let's call that 949. I'm going to store that as B. Now I'm going to do the cosine of that big ugly thing. So cosine of 4 times 10 to the 5 times 10 times 10 to the -6 times 180 over pi plus the angle of x plus 180. This big thing here looks like 0.381. And so now I'm going to have, let's store that as C. And so I would have A times B plus C. And I get negative 2.694 or 6938 and some change watts, which agrees with what I should have got. So the reason why I chose to work this problem out with you guys was twofold. A, I wanted to illustrate exactly what I was talking about earlier. We're simply taking the results of our frequency domain circuit analysis and plugging the parts into our equation as we need them, okay? And B, I wanted to illustrate that we have to pay a whole heck of a lot of attention about the units, so to speak, of our angles inside of our cosine functions, because our calculators can only handle angles in radians or degrees, certainly not both at the same time. So we need to be very careful and remember to apply conversion factors where appropriate so that our calculator isn't just giving us nonsense, right? Because the calculator is not going to tell you, hey, this angle was in degrees, this other one was in radians, you shouldn't add them together. It's just going to say whatever, whatever, and give you a number based on what you put in, right? Your calculator is only as smart as the person entering the numbers into it. So you got to pay attention to the unit of your angle. All right. Any questions about this wall of math before we get back to normal lecture stuff? Yes, ma'am. Sure. So if we look back at our original circuit diagram, oh, here we go. I'm going to draw this voltage V here as well, right? There's nothing wrong with me putting it here because all of the elements are in parallel. The positive, the current 0.1 angle 0 is flowing into the negative polarity terminal first. Because we were asked to find absorbed power, we actually need the current that is flowing into the positive polarity terminal, which would be this current flowing down. To change the direction of my current, I simply shift its phase angle by 180 degrees, because 180 degree shift is the same as multiplying by -1. Anybody else? All right. So, sorry, wrong thing. So we kind of stumbled onto the concept of average power a little while ago. And so now we're going to more formally describe that because you're going to need to understand some of these relationships for what we're going to be doing in our subsequent class meetings. Okay? So I'm going to call this part right here average value of periodic functions. So let's say that x of t is a function with period capital T. If I can define a period for this function, then quite obviously it must be a periodic function, okay? The average value of this periodic function is going to be the integral of our function x of t with respect to time. We are going to integrate it over exactly one period. And then we are going to divide by the length of that period. and that will give us the average value of our function. This is something that you should have seen before, but if not, it's not particularly difficult to understand. If we have a function and we take the integral over one period, and then we divide by the length of that period, that's the total area divided by the interval is just the average value of that function. Okay. So let's apply this to our power relationship. So the average value of our power is going to be 1 over t times the integral from 0 to t of p of t dt. Which is going to be 1 over t times the integral from 0 to t of 1/2 the magnitude of our voltage, magnitude of our current, cosine theta v minus theta I, plus 1/2 magnitude of our voltage times the magnitude of our current, cosine twice omega t plus theta v plus theta I, close this thing off, dt. So because the integral operation is a linear operation, I can actually just split this thing up into two integrals. Right? So that's going to look like 1 over t times the integral from 0 to t of 1/2 Vm Im cosine theta v minus theta I dt plus 1 over t times the integral from 0 to t of 1/2 Vm Im cosine twice omega t plus theta v plus theta I dt. Let's look at this second integral first, okay? And to help us out, I'm going to attempt to draw a picture. Let's say, just for simplicity's sake, that theta v plus theta I added together come out to be 0 degrees, so that my phase angle is effectively 0, and I don't have to shift anything because that's just going to make my drawing look even worse. So the AC portion of this thing is just a sinusoidally oscillating signal. Okay? So something looking like this, except that it should be the same maximum value. There we go. Our period is just the distance between our positive peaks. Okay? So if I were to integrate this function over exactly one period, what would the result of that integration be? 0, because exactly half of the time we're above 0 and exactly half of the time we're below 0. So it's just going to look like 0, right? So all of this area is canceled out by all of this area below the curve. So this whole integral right here is simply 0. I'm going to say this now with a full understanding that you guys are going to forget it before Monday, that when we do this again, the integral of a sinusoidal function over any integer number of periods is always 0. So as long as we're integrating over exact period lengths, it's just going to come out to be 0. We're going to use it again. I fully expect you guys to forget. It's okay. So that just leaves us with this business on the left. Well, we discussed earlier that all of those things are constant. Right? So we could actually pull all of that out of the integration. So we would have simply 1 over t times 1/2 Vm Im cosine theta v minus theta I times the integral from 0 to t of dt. What's the integral of 0 to t of dt? Capital T. So this capital T gets canceled by this 1 over capital T, and we're just left with the exact same thing that we observed previously. The DC portion of our instantaneous power is our average power. We got there intuitively just by looking at our graph, and now we have formally mathematically described why that is also true. Okay. All right, so that is enough out of me for today, unless anybody has any questions. If you have any questions, I'd be happy to answer them. If not, please work on your in-class assignment, problems 1 and problem 3. And yeah, have a good rest of your Friday.